So here we are at 9.2, analyzing rational functions. First thing I'd like to say is that 9.2 is not nearly as long as 9.1. It will just take one video for us to get through this, and it will be, I think, relatively painless. I think we'll be doing just fine. The question says, sketch the graph of f of x is equal to x plus 1 over x squared minus 2x minus 3. The first thing that we need to remember is to, if you can, factor the numerator and the denominator. So in this case, isn't this nice that the denominator has been factored for us right here, x plus 1 times x minus 1. Now the first thing you'll notice is this x plus 1 in the numerator and the x plus 1 in the denominator, we can cancel that out. What I'm doing is I'm dividing the top and the bottom by x plus 1. So as a result, we get 1 over x minus 3. Now the thing to watch out for is I can't be dividing by 0. So I have to make sure when I do that action of dividing by x plus 1 that I'm not dividing by 0. And so when would x plus 1 cannot be equal to 0, so therefore x cannot be equal to negative 1. So what I've done now is I've changed my original function, this one here, into this function down over here. These two are identical mathematically, this function and that function. If you don't add the x is equal to negative 1, is not equal to negative 1, pardon me, then you are in error. So you need to add that little restriction to the domain here. That's really what that is, comma, x is not equal to negative 1. So what does that look like when we graph it? Well, the next line says this is identical to this except for there is a point of discontinuity when x is equal to negative 1. It means we're not allowed to make x equal to negative 1. The domain of that function is x can be all real numbers, but x cannot be equal to negative 1. A point of discontinuity is a point at which the graph of a function is not continuous. This point is missing from the graph, and so we represent it with an open circle. Points of discontinuities are often referred to as holes. So I often use the word hole rather than point of discontinuity. Perhaps it's because the word hole is so much shorter. So let's see if we can graph this. We have y is equal to 1 over x minus 3, and it says that x is not equal to 1. So first of all, let's find where the hole is. The hole is at, so I know the x value. The x value is 1, but I don't know what the y value is yet. So let's figure that out. If I take this, y is equal to 1 over x minus 3, and I substitute a 1 in for x, then I'm going to get 1 over negative 2, so I'll get a negative 1/2. So my y value here is going to be equal to negative 1/2. So when I take x is 1 and y is equal to negative 1/2, right here I'm going to put a little circle to show my hole. Okay, now from this point it's just graphing as if you would normally graph this function right there. So how would I graph the y is equal to 1 over x minus 3? And I'm reminded by the fact that the parent function would be y is equal to 1 over x, except I have to move it over 3 to the right. So I will draw my vertical asymptote at x equals 3 because it went 3 to the right. I'll draw my horizontal asymptote right along this axis here, like that. And now I want to think about the points that I want to make. I want to make points that multiply out to this 1 up here. So starting from here, my x and my y value can both be 1. You'll notice that normally I could go over 2 and down 1/2, but I have a hole right there, right? So I can go over 1, 2, 3 and down 1/3, and so on. Looking the other way, I can move left 1/2 and down 2, left 1/3, down 3, and here I'm going to get my curve. So it looks like the kind of a question that we would have done in our last lesson. The only difference here is we have that hole. Moving on the upper right of the intersection of those two asymptotes, 1 and 1, 1/2 and 2, and so on. So I get this kind of a behavior. Alright, so that's what we get as a result. And so what have we graphed? We have graphed this function right here. Moving on to the next point, it says we need to sketch the following graphs. So the first one is x squared minus 5x plus 6 all over x minus 2. Okay, so the first thing is we would need to factor. So thinking about that numerator here, thinking about the numerator, we want two numbers that have a product of 6 and a sum of negative 5. So it seems to me they're going to have to both, let me see, negative 5 and negative 1 would work, wouldn't they? Because they have a product. Oh, no, wait a minute. Going to have to think about this one. That one didn't work. How about negative 3 and negative 2? Yeah, that would work, because if I multiply them out, I get a positive 6, and if I add them together, I get a negative 5. Okay, so the next step here is, let's write it out in factored form. We get x minus 3 multiplied by x minus 2 all over x minus 2. Okay, let's clean up my mess here. Now I'm going to say, alright, now this is the same thing as y is equal to x minus 3, except what I have done here is I have divided the top and the bottom by x minus 2, and I will say that there is a restriction in the domain that x cannot be equal to 2. So in other words, I'm going to have a hole at, and I know the x value is 2, and I need to find out what my y value is. So I say y is equal to x minus 3, but I'll put a 2 in for that x, and so my y is equal to negative 1. So again, to find out where the hole is, I take my new version of the graph. I wouldn't put it in the original one because I'd be dividing by 0. So I take my y is equal to x minus 3. Y is equal to x minus 3, and I put my x value of the hole in there, and I find out what the y value is. So I'm going to graph that right away. I'm going to put 2 and negative 1 is where this hole is going to be. So there is that hole right there. Now, so otherwise, I'm just going to say, hey, how do I graph y is equal to x minus 3? Well, it seems to me it's something that has a y-intercept of minus 3, and it has a slope of 1. So I'm going to get a line that goes up. Careful of that hole. Okay, and now I'll put, not doing a very good job, put those arrows over there. So that's what that line looks like. It's just a straight line of y is equal to x minus 3, except for there's a hole at 2 comma negative 1. So what is the non-permissible value? X cannot be equal to 2. The x-intercept, it looks like it's x equals 3 just from my graph. The y-intercept, y is equal to negative 3. The vertical asymptote, there is none. The horizontal asymptote, there is none. Point of discontinuity, that is the hole that I was talking about, so that is at 2 comma negative 1. What is the domain? Well, x is all real numbers except for x cannot be equal to 2. Otherwise, we are good to go with all real numbers. There we go. Made it look really nice. The range, similarly, y cannot be equal to, but it's not 2, it's negative 1. Otherwise, it can be all real numbers. And I'm really messy, pardon me. Now it says explain the behavior of the graph near the non-permissible value. So in the past, when we had non-permissible values, we had like asymptotes. We had typically a vertical asymptote where we couldn't have an x because it was in the denominator. This is a little bit different here. So I'll say as x approaches, and what is approaching? 2, y approaches negative 1. Okay, but it never actually gets there. So because x can't be 2, but as x gets closer and closer to 2, y gets closer and closer to negative 1. So that's the first part here. So that was the answer number 1. The second one here, trying to switch to green. So here, part number 2, where it says explain the end behavior. The end behavior, well, there are no horizontal asymptotes, so we don't even have to talk too much about this. We can say as x gets larger to the right, so as x approaches positive infinity, so as x goes to the right, y approaches positive infinity. Okay, or another way we could say it is up in quadrant 1. Okay, that's just another way of talking about it. The other one is as x approaches negative infinity, y also approaches negative infinity, or another way we could say is down in quadrant 3. So two different ways of talking about it. This one has the fancy arrows and approaching idea. This one just says it goes up in quadrant 1 and down in quadrant 3. For our next example, they give us we have a polynomial in the numerator and a polynomial in the denominator. So the first thing we're going to want to do is to factor both the numerator and the denominator. So looking at this, I'm at this numerator here. To factor it, I'll just do my work over here, x squared minus 3x minus 2. So I want to break this minus 3x into two numbers, and I want them to have a product of 2 times negative 2, a product of negative 4, and a sum of negative 3. So what could those two numbers be? I'm thinking a negative 4 and a positive 1 would work out. So here I'm going to write minus 4x plus a 1x plus an x. Now I'll factor out these two, factor from the first two terms a 2x plus, and maybe if I write a 1 here, x minus 2 kind of makes it a little bit easier to see. So that's what that looks like. So my numerator is going to look like 2x plus 1 multiplied by x minus 2. Now thinking about my denominator, I have x squared minus 3x plus 2. It's a little bit simpler. I want two numbers whose product is plus 2 and whose sum is negative 3, so it seems to me they have to both be negative, x minus 2 and x minus 1. So we'll put that in the denominator here, x minus 2 multiplied by x minus 1. Okay, and I think I got a fancy little cleanup job here to do. Oh, didn't quite get it. Let's see if I can finish it up here. Oh, come on. All right, there we go. Thank you for your patience. Now I would like to cancel out the x minus 2 and the x minus 2, and when I do that I have to add the restriction to the domain and say that x cannot be equal to 2. So now I'm down to y is equal to 2x plus 1 all over x minus 1, where x cannot be equal to 2. So now it looks a lot like a question that we did in 9.1, where what I need to do is convert this to make it look a little bit more like something like this, 1 over x plus some number like that, or maybe it's going to be a 2 over x. I think it's going to end up being a 2. Let's see. So how did I do that? I said y is equal to, now x minus 1 is in the denominator. Looking at my 2x, what number would I like to put next so that I could factor out an x minus 1? I think I needed a minus 2. Except that it should be a plus 1. So how can I turn that into a plus 1? I would say I would add 3 to it. So in my next line I'm going to say y is equal to 2 times x minus 1 all over x minus 1 plus 3 over x minus 1. And so I will get, at the end of the day here, y is equal to 3 over x minus 1 plus 2. Now I really should be careful to keep my x cannot be equal to 2 all along the way. So I'm going to go back and be good and write x cannot be equal to 2 here, x cannot be equal to 2 here, and x cannot be equal to 2. So speaking of the fact that x cannot be equal to 2, really we're going to have a hole, aren't we? I'm going to do my work over here. So let's think about this hole. At, now the x value is going to be equal to 2, but what will the y value be here? Let's try it again. What will the y value be? So taking this definition here, I'm going to say that y is equal to 3 over x minus 1 plus 2, but now I will substitute a 2 in for x. So I'll say y is equal to 3 over 1 plus 2, so y is equal to 5. Oh, that's a messy 5, but I'll just put a nice neat 5 over here. So we have a hole at 2, 5. So going over here, 2, 5, up here is where my hole is, right there. Now, besides that, we're going to graph this y is equal to 3 over x minus 1 plus 2. So what happens? Well, if it was just 1 over x, I would have a horizontal asymptote and a vertical asymptote along the axes. But here I need to shift 1 to the right, so I have a vertical asymptote at x equals 1. Getting a little messy here. And I have a horizontal asymptote at plus 2 because I need to move up 2. So here is my horizontal asymptote. And now because of this 3 up here, I need to go and think about, starting from here, pairs of numbers that multiply out to 3. So 3 and 1 work well, and 1 and 3 would, but I have a hole there, so I better not put 1 in there. 2 and 1.5 would work, and then 1.5 and 2 would work. Okay, so I get those nicely. I'm going to draw this out, and it even goes past as well. And then on the other side again, I'll say 1, 2, 3, and 1, 1, 2, and 1.5, 1 and 3. Oh, sorry, 1 and 1, 2, 3, and maybe a half and 1, 2, 3, 4, 5, 6 over there. So now I get again this shape, but there's no hole, there's no point of discontinuity on this side. So just to come out a little bit. Alright, so what is my non-permissible value? My non-permissible value is x cannot be equal to 2. The x-intercept, looking at my graph over there, I'm not quite sure exactly what it is. I'm going to have to do a little bit of work to figure out what my x-intercept. So just a reminder, what is x-intercept? It is what is the value of x when y is equal to 0. So my function here, I have a few choices, some different variations of my function. Here's my original one. If I put a 0 here, this looks very complicated to try to figure out what my answer is, but you know, that is one method I could use, or I could go and take a look at some of my other versions. I'm going to take my very last one here, where I've got y is equal to 3 over x minus 1 plus 2. And again, I'm going to say, what is my x going to be when y is equal to 0? So I'll say 0 is equal to 3 over x minus 1 plus 2. I'll subtract 2 from both sides. Here, I'll move in a little bit. Subtract 2 from both sides, and then I get 3 over x minus 1. Now, if I multiply both sides by x minus 1, multiply out the 2, negative 2x plus 2 equals 3. So negative 2x is equal to 1. X is equal to negative 1/2. Let's just see if that makes sense. Yeah, that looks like it's probably about 1/2. I just move that over a little bit. So my value here is negative 1/2. To figure out my y-intercept, it's a little bit easier because it was a negative 1. So in this case, my x is 0 and my y is equal to negative 1. My vertical asymptote is at x equals 1. My horizontal asymptote is at y is equal to 2. The point of discontinuity, that is the same thing as saying the hole, that is at 2, 5. And what else do we have left here? We have the domain and the range. I'll just keep it simple. I'll say that x cannot be equal to 2 and y cannot be equal to 5. Otherwise, it's all real values. Now it says explain the behavior of the graph near the non-permissible values. Well, I can say as x gets closer and closer but doesn't quite meet, as it approaches 2, then y approaches 5. That's the first part. And then the second part, number 2, my answer for number 2 is over here. Explain the end behavior. There are more non-permissible values than just that. I could also say as there's the asymptotes, right? Let me switch back to blue. So looking at the asymptotes, as x approaches positive 1, then y approaches either positive or negative infinity, depending on which way we're looking at it. And the other one is as y. Now those are our end behavior over here. As y approaches positive infinity. So what happens here as y, this is the end. So what I'm doing is I'm looking at off to the right what happens here as x approaches positive infinity, then y approaches 2, and as x approaches negative infinity, then y also approaches 2. Okay, how did I do? For the domain, actually, I should add here, x cannot be equal to 2, and also x cannot be equal to 1, right? And for my y values, also I have y cannot be equal to 5, and also y cannot be equal to 2. I also have to include my asymptotes. Alright, I think we have, is it just one more question here? Let me just peek ahead. Yeah, one more question before we're off to go. Okay, so first things first is we're going to factor the numerator and the denominator. We can't really factor the numerator here, it's just x squared. But in the denominator we have a common factor of x, so I can go like this, x minus 4. And it's at that point we can say, hey, there's a common x to both the numerator and the denominator. So when I divide both the numerator and denominator by x, I'm going to get an x over x minus 4. So what did I divide by? I divided by x, so I have to be careful, and I'll say x cannot be equal to 0. So this is what it's going to look like. I'm going to have a hole at 0. Now my x value is 0, and I have to figure out what my y value is. So just look at this. If I put in a 0 for x, I get 0 divided by negative 4, which is going to be equal to 0. So I'm going to have a hole at the origin. Okay. Now let's put this into a slightly better way of trying to graph this. So if I think about this, x over x minus 4, to factor this more, to find a common x minus 4, I would have to put a minus 4 there, but there's only an x there, so I'd have to put a plus 4 there as well. So f of x is equal to that, and I'll add my x cannot be equal to 0. So I usually write this as x minus 4 over x minus 4 plus 4 over x minus 4. Do you see what I did there from that line? This line over here, I just separated that 4, and still x cannot be equal to 0. So I'm going to switch this around. I'll put this term first. 4 over x minus 4 plus, now this term here is 1, where x cannot be equal to 0, and this is f of x. So this is the part that I'm going to be used to graph. So I've got a hole at 0, 0. So there's the hole there. And I have a asymptote. It's moved over 4 to the right, so I'll have a vertical asymptote at 4. And because of that plus 1, I'll have a horizontal asymptote at 1. And now for my graphing part, I'm going to start from where the asymptotes meet, and I want to find pairs of numbers that multiply out to 4. And you can see how that hole would line up: 1, 2, 3, 4, and 1. So there's one of my spots. Also 2 and 2, and 1 and 1, 2, 3, 4. So here's the way the graph looks. Something like that. I kind of missed that spot. And same as over here, I would get 1 and 1, 2, 3, 4. And it's kind of harder to get 1, 2, and 1, 2, so another one would be over there. So this kind of goes like this, right? A little bit off the page. Doesn't hit very well. And I think that's all the stuff that we need. We can put in what is the non-permissible value here. X cannot be equal to 0. The x-intercept, well, 0, 0, and the y-intercept 0, 0. The vertical asymptote is going to be at x is equal to 4. The horizontal asymptote is at y is equal to 1. The point of discontinuity, oh, but wait a minute, it does not actually hit the x-axis. So I kind of made a mistake here, didn't I? There's a hole right there, so it doesn't ever hit the x-axis or the y-axis. So I put none here. That's kind of cool, because that's a point of discontinuity. There's a hole right there. What is the domain? What are all the possible x values? Well, x can be anything except for the hole and that asymptote. So x cannot be equal to 0, and x cannot be equal to 4. Alright, I should really dress that up better. I'll say, okay, curly brace x such that x is not equal to, and I can say 0, 4, that's okay, but x is a member of all the real numbers. Okay, just to be a bit more diligent. Now for the y values, y cannot be equal to 0, and that also y cannot be equal to 1. Alright, and now there is your homework. I hope you enjoy those questions. They're kind of fun, and I'll see you in class.